This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Okay. Let's get started, shall we? I'd like to know what these new curtains are for. Nobody here knows, do they? What? What are they for? I feel like I'm supposed to burst out and do some play or something. All right. What have we got today? I haven't got much housekeeping today. It's an even week. That means it's pracs this week, so don't forget to go to your pracs. And you get to work on your project again. So the more that you've done before you actually go there, the more help you'll be able to get from your tutor for the questions that come later on. It's Tute 7 this week because it's week 8. And because it's week 8, I have some fantastic news. This is the last week before the break. Woohoo! And then we get a couple of weeks off. Well, you get a couple of weeks off. Does anybody have any housekeeping questions? No? Okay. All right. Who's talking now? These guys here and you girls up there and who else? Everybody else. All right. So today we're going to finish off this integration with trig substitution stuff, and we are going to do loads and loads and loads of examples today. And near the end of the lecture, near the end of the second hour, we're going to do something a little bit fancier with these trig substitutions. Okay, but first we're just going to do lots of examples. So remember what we're doing is we've got a function like this to integrate where you've got something on the bottom line which is a 1 or a number plus or minus something squared, right? And you can't do a u substitution because the derivative of this thing isn't sitting up with the dx, okay? There's no x on the top line, so you can't do a u substitution. So we're going to do a trig substitution where we can pick one of these six things. So there's the trig functions and there's the hyperbolic trig functions. And so with this one here, you've got 1 plus something squared, so you'd match it up with this one, 1 plus something squared, or you can match it up with this one, 1 plus something squared here, okay? Then you can do your substitution, use the identity that you chose to use. Make sure you change your dx into a d theta as well. And after you've done that substitution, you should end up with something that's really easy to integrate. It won't always be as easy as this one, but it should be pretty easy. If the number in that denominator is not a 1, you can multiply these identities by whichever number you like. Multiply the whole identity and then do the same thing. The only other thing is make sure your answer is in terms of x. So sometimes it's easy to change like this one, and sometimes you've got to do those little triangle things or use the identities again to change back, and we're going to practice both of those things too. What else? We did that one. There was something else I wanted to say. I don't know what it was. Okay, so we haven't looked at this page yet, but this page is basically saying don't forget to turn your answer in terms of theta back to an answer in terms of x. And you can do that by using a right-angled triangle or by using the identities again. And that's what this page says, but I think it's much easier just to do it. So we're just going to do it in some examples. I can't remember what I was going to say now. Okay, lots of examples. They just keep going on and on. Before we do these examples, though, I'm going to spend some time talking about how to find the sine or cosine or tan of the little angles that you should know. So you should know something about pi on 3, pi on 6 and pi on 4, and you should be able to extrapolate that for the domain that you need for the inverse functions. Okay, so that's what we're going to do first. Okay. So the angles that we're interested in is pi on 3, pi on 6 and pi on 4. Now some of you probably did this at school. Some of you probably memorised it at school. On the cheat sheet, sorry, I've got the sneezes today. On the cheat sheet, on the formula sheet that comes with your exam, there are some of the angles there, but you need to know how to use them to get the other angles that you don't know. Oh man, I don't know if I've got hay fever or a cold coming. All right. So instead of remembering the sine and the cosine and the tangent of these 3 angles, so that's 9 things so far, and then remembering how to extrapolate it into 4 quadrants, so how many things is that? 36. So instead of remembering 36 things, I'm going to show you how to remember it with just 2 little triangles and remembering the graphs of the sine, cos and tan functions. All right, there is one function here which is a bit tall and a bit skinny. This is called the 1, 2, 3 triangle. 1, 2, 3 triangle. If you wanted to make a triangle though with sides 1 and 2 and 3, that's not going to work with a right angle, because if it's a right angle triangle you need to satisfy Pythagoras. Okay, so all you have to do, what do you have to do? Put a square root on here. Okay, because then I've got 1 squared is 1, 2 squared is 4, root 3 squared is 3, and I can combine those numbers in a way that satisfies Pythagoras. Right? This is the shortest one. That's 1. 2 is the longest. 2 is the longest one, and the square root of 3 is the other one here. And you can check that that satisfies by Pythagoras. If you square this, you get 1. If you square this, you get 3. 1 and 3 is 4, which is the square of that. Okay. So it's a 1, 2, 3 triangle, and you just have to arrange them in such a way that you satisfy Pythagoras. Okay, this is the pi on 3 and pi on 6 triangle. Now this is a fat angle, and this is a skinny angle, because you divided pi into more pieces. Imagine you have a pi and you divide it into 6 pieces. So I've got pi over 6 up here, that's the skinny angle, and pi over 3 here, and that's the fat angle. Okay? Once you have that written down, you can find out almost everything you need for those 2 angles. Okay? When I did my exams at school and in my undergrad, I would walk into the exam room and you get a scribble paper, right? And I would just draw this triangle straight away on the scribble paper, and then it's there, and I've got it for whenever I need it. The other triangle, which isn't very much like a triangle, is the 1, 1, 2 triangle. And to make that match Pythagoras, I better put a square root there. So these 2 sides are the same, and the hypotenuse is the square root of 2. If these 2 sides are the same, then these 2 angles are the same. By the way, that's a right angle. So this is going to be pi on 4, and this one's going to be pi on 4. Okay. The other thing you need to know is SOHCAHTOA, or some old hags, which I prefer. So some old hags can always hide their old age. Okay? That's much better than SOHCAHTOA. Who knows how to even spell SOHCAHTOA? Alright, some old hags can always hide their old age. So this tells you that sine theta is like opposite over hypotenuse. Cos theta is like adjacent over hypotenuse. Tan is like opposite over adjacent. Okay. Alright. So now we've got the two triangles and we've got our some old hags. All you need to know next is the sine curve. Whoops. Oh, you know what I mean. This is why I'm not a geometer. Alright, this is 2 pi and this is pi, and then it of course can go backwards in the same way. So this is sine. Cos starts at 1, and you have to do a full cycle to get to 2 pi. So that must be 2 pi and that must be pi. Okay, and of course it goes the same in the backwards direction. And the tan graph, I'm only going to draw the middle one. This is cos theta. And this one's quite skinny. It's pi over 2 and minus pi on 2. And you can keep going for as many of these little curves as you like. You know it has to be pi on 2 because tan is sine over cosine. So it's going to go up to infinity when cos goes to 0, which is at pi on 2. Okay, so that's why you've got this asymptote at pi on 2. Okay. And from that information, which really, I mean, I've done it, I'm going to say I've done it quite nicely. I've done it there fairly neatly. When you do it on your scribble paper, you don't have to do it that neatly at all. It takes like 30 seconds, okay? And then you've got it there. And you can work out whatever you need, all right? So if I want to work out the sine of pi on 6, well, I go to, here's pi on 6, and sine would be opposite over hypotenuse, so it's a half. And it's as easy as that, okay? What if you wanted to do sine, let's do one that's a little bit harder, sine of 7 pi on 6, sine of 7 pi on 6, well that's more than 1, that's like 1 and 1 pi on 6, that's here. Pi on 6 is the important angle because that's how far what am I trying to say? If I'm this far away, this value here is going to be the same as this value here, but negative, okay? So that the distance you are away from pi or 2 pi or minus pi, that's the angle that's important. So here I'm pi on 6 away from pi, so pi on 6 is the important angle, so it's going to be a half, but here sine is negative, so I need a negative sign, okay? Now, you get a chance to practice this in your tute this week, I think it's this week, or maybe it's next when we get back from the break. But anyway, you get a chance to practice this in your tute, all right, because this is something you need to be able to figure out. As I said, some of it's on the formula sheet, but not all of it, okay? So make sure you know what's there and how to use it. All right, does anyone want to ask any questions about that stuff?
The inverse, is that just around the answer?
Say that again.
How do you find the inverses around?
Okay, so if you want to do, let's do this. Let's do let's do arc cos of 1 over the square root of 2, right? So what you do is you look for where 1 over the square root of 2 is going to be adjacent over hypotenuse. So 1 over the square root of 2 is here, adjacent over hypotenuse, and here's the adjacent one. So that's pi on 4. Okay? If I wanted to do a minus 1, let's do this one. of minus 1 over square root of 2, right? Ignore the minus sign to start with and just worry about the 1 on root 2. So the 1 on root 2, well, that's just what we did. We found an adjacent over a hypotenuse that was 1 over root 2. So the important angle is going to be pi on 4. Let's just write it here for a moment. But we actually want it to be negative. So we look at the cosine curve and you think about the domain which is included for the inverse function, and it's this part here, right? So you want the part that's negative, which is this part here, that has an important angle on pi on 4. So it's going to be 3 pi on 4. Yeah? That's it. Okay? Okay. So you get a chance to practice this in your tute, so make sure you practice that. Okay? Does anyone want to ask any other questions? No? Okay. All right, what are we up to? We're up to the first example for the day, 35. Oops. Okay. All right, this is a little first order ODE and it's separable because I can get all the x's on one side and all the y's on the other side. All right, I'm going to write it like this. 9 plus x squared. Okay, and so once you've separated, then you can integrate one side with respect to y and one side with respect to x. Okay. Okay, so this is when we have to do trig substitution. When we finished all the integration techniques, I'm going to talk about how to pick one. And you have to pick them in order of easiest to hardest, right? So the easiest one is a u substitution, but you can't do a u substitution because the derivative of this isn't hanging around anywhere, right? So we're going to have to do a trig substitution here. And the reason we have to do a trig substitution is because you've got this power out here, or even out here, a minus 1 at that, right? And you can't just put it on this one and put it on this one separately. Okay, it doesn't work like that. All right. So now we have to pick one of these trig identities to use. Which one will we use? Which one? Which one can you use from here? Yeah, tan squared, or which one from here? The shine one, that's right. So you could use this one or this one. And I'm going to talk about which one to choose later on, but I did this one already and this one's the easiest one. Okay? So we're going to use 1 plus tan squared theta. Okay, but we don't have a 1 plus, we've got a 9, so I'm going to multiply this thing all the way through by 9. Now, the 9s match, the plus matches, that means the x squared must match this thing here. So x is going to be 3 tan theta, because when you square the 3, you're going to get the 9. Okay? Make sure you pay attention to that. 3 sec squared theta d theta. Okay, so you have to change the dx as well. So we're going to change dx to d theta. And now we've got here 9 plus x squared. That's going to be 9 plus 9 tan squared equals 9 sec squared theta, and you get that from the identity that we picked. Okay. All right, now we can put everything in. So y on this side equals 9 plus x squared is going to get replaced with 9 sec squared theta to the 3 halves, and dx gets replaced with 3 sec squared theta d theta. Okay, so now that we haven't got two things added together, now that we've just got things multiplying each other, we can bring this power inside the brackets. All right, so I'm going to take this 3 outside on the top there, and I'm going to take this number outside too when I figure out what it is. So the 2 on the bottom line is like a half, that means square root. So the square root of 9 is 3, and then we want to raise it to the 3rd power. Everyone get that? Everyone's happy with that? 2 on the bottom means square root, which is 3, and then we want to cube it. Okay. And the same thing here. So we get, oops, no we don't. We get sec cubed, bless you, and sec squared theta d theta. Okay. 1/9 integral. Now here, if I cancel some of these things out, I'm going to end up with a sec theta on the bottom line, and sec theta is 1/cos theta. So this is just going to be cos theta d theta. Okay, and we can integrate that because we know what to do here. There we go. Okay, so here's the answer in terms of theta, but you want to write the final answer in terms of x. Now, you've got two choices with the trig functions. You can either do a little triangle or you can use the identity, right? Now, here was the substitution we made. So we have to link tan theta with sine theta in order to change this one into x's, right? Now, none of these identities here link tan theta and sine theta. I could go through 2 steps here and then I'll be able to link them, but I can't link them with just one. So because of that, I'm going to use the triangle. Okay, so the substitution I made said that tan theta was x/3. Okay, and tan, some old hags can always hide there, old age. Okay, opposite over adjacent. So I can make up my own little triangle here with a theta, and the opposite side should have x, and the adjacent side should have 3. And then I can use Pythagoras to work out the hypotenuse, so it should be 9 plus x squared. How you fancy that? That was in the question. Remember I said your answer will always have some part of the question inside it? This is it here. All right, now sine theta is what we want. Some old hags. So the opposite here is going to be x, and the hypotenuse is going to be 9 plus x squared. Okay, so now I can convert sine theta into x's. Equals 1/9 let's see. Okay, and that's your answer in terms of x, or at least for the integration part. Does anyone want to ask any questions about that so far? No? Okay, the other thing with this question though, it's got a boundary condition here, so we've got to substitute this in to find out what the c is. Okay, but 4 equals 1. So 4 is the x value, and 1 is the y value. So let's put that in. 1, 4. Now 9 and 16 is 25, square root is 5, so that's just 4/5. Bless you. I'm going off on it. There we go. Okay, does anybody want to ask any questions about that one? No? Okay. Everybody's done, I think. Okay. All right, here's another question. Example. Huh? This doesn't look very much like a circle, does it? It really does on my piece of paper. That's a bit more circlish. All right, consider this little circle here of radius A. It's still very ovally, but anyway. What fraction of the circle lies in that little shaded bit, okay? So instead of finding that whole area, what I'm going to do is find this area here, and I'm going to times it by 4, okay? All right, so the area is going to be 4 times whatever this is. Now we just have to figure out what that is. Okay, so when you're finding an area like this between a function here and the x-axis, what you would do is you would take the integral of this function here over this little domain here, okay? So we take the integral. Now this function here, just in this little area, is going to be y is equal to a squared take x squared square root. The reason I said just in this little area, because in this area here, you would take the negative square root. Okay, in this area here, you want to take the positive square root because you're at the top of the circle. Okay, so we've got something here that looks like a squared minus x squared dx. And we're going to integrate from 0 to a over 2. Whoops, 0 to a over 2. Okay. Now you can't do a u substitution with this one because of that a squared minus x squared is all tangled up under the square root. So that means we have to pick a trig substitution. Which one will we pick? Which one will we pick? Yeah, sine squared or what else? The tangent squared, that's right. So this one or this one, because we've got a number squared minus the x squared, and the x is what we want to pay attention to, which is the easiest one. The sine squared one's the easiest one, okay? I'm going to talk about that in a moment. All right, so we want to multiply that whole identity by a squared, right? So we get the a squared minus a squared sine squared theta, so that we get this a squared here to match with this one. Okay. Okay, so the a squareds match, the minus matches. That means that a squared sine squared must match x squared. So here I want a sine theta. A cos theta d theta. And then I'm just going to work out what this is once I transform it. A squared sine squared theta. There we go. Okay, so now we can substitute this stuff in. So I've got a 4. Now a squared minus x squared is going to be a squared cos squared theta, whoops, with the square root. And then we've got dx, and that's going to be a cos theta d theta. Okay, now I can't just write 0 and a over 2 here by themselves because these are x bounds and they match the dx here. And now I've got a d theta. So I've got two choices. I can change these into theta bounds, or I can just make a note that there's still the x bounds, and that's what I'm going to do. Okay, you have to do that. You had an x integral, now you've got a theta integral, so make sure you change your bounds. Right, 4. I'm going to get an a from here, and I've got an a from here, and those things are both just constants, so I'm going to zip them out through the integral sign, and there's 2 of them, so I've got an a squared. And then I can take the square root of this, and I've got a cos here, and I've got a cos there. A over 2. Okay, so now we have to integrate cos squared with respect to theta. How are we going to do that? Yeah, double angle, half angle formula. So this one here is going to change into a half 1 plus cos 2 theta. I'm going to zip the half out the front. 1 plus cos 2 theta. Whoops, x equals 0, x equals a on 2 d theta. And these things here we can integrate. We can integrate 1 and we can integrate cos 2 theta. So what do we get? 2a squared theta okay. So you still need the x equals there because I've got an expression in terms of theta and my bounds are still in terms of x. Okay, so we've now got to substitute these bounds in. Now we've delayed making a decision about what to do until now. So now we have to decide, do we want to change this to x or do we want to change these to thetas? This is a little bit hard to change to x because this is a trig function with a double angle in it, and our transformation, our substitution just had a single angle in it. So you can make that change there, but it's pretty tricky. So I'm going to change these things to theta values. Okay? So let's do that. When x is equal to 0, use our substitution. So you would get 0 equals a sine theta. And you want to know what value theta will take, right? Theta is going to be 0. So when x is 0, theta is 0. Now do the top one. You get a over 2 equals a sine theta. Okay, and we want to know what value theta takes there. Okay, so the a's are going to cancel out. And we want to know what value of theta gives a half when you take the sine of it. Oh look, it's right here, we already did this one. So this is when you go back to your triangles, right? And you'd say, well here I can make a half with that. Sine is equal to opposite over hypotenuse. So which angle is this opposite over hypotenuse? Well, it's this one here, because that's the opposite side. So it's going to be pi on 6, okay? Right. So this becomes theta. There we go. All right, so now we just have to substitute these things in. 2a squared take away 0. Okay, I put it away too hastily. Okay, so now we want to know what sine of pi on 3 is, and you can go back to your triangles. Here's pi on 3, and we want the opposite. Opposite? Yeah, we want the opposite. Opposite over hypotenuse, so it's going to be root 3 over 2. Root 3 over 2, and I've got a 2 there, so it's going to be 4. There we go. That's the answer. So that's the area that's in that shaded section in the middle of that circle. All right, does anybody want to ask any questions about that one? No? Okay. Pardon? There's not a constant because it's a definite integral. So you know the bounds. If you did a plus c, what would happen is you'd have a plus c in here, and then when you make your substitution, you'd have a plus c and you'd have a minus c, and they cancel each other out, so it doesn't matter. Okay, next one. All right, now comes the time where I'm going to talk about how do you know which trig substitution is to use. Okay, so this one here, okay, if a was equal to 0, this integration would be dead easy, right? Because you can just, it's just like a polynomial one, increase the power by 1 and carry on so forth. Okay, but it's not. All right, so first of all, let's identify which 2 we can choose. Which 2 can we choose for this one? Yeah, so we can choose this one, or we can choose this one, right? And the question is, which one do you choose? That's the tricky part. The answer is, you really don't know, and there's really no way of telling. That's the bad news. The good news is, if you pick the wrong one, it's not very long until you find out you picked the wrong one. And then you should be aware that you can make the choice to say, I've picked the wrong one, try the other one, okay? So you're not going to waste a lot of time if you do choose the wrong one. So let's use the trig one first. Okay, so this is the one that we're going to try. You can already tell it's going to be wrong because I'm saying let's try it. Okay, so the a squareds match, the minus matches, that means x squared has to match this thing here. X equals a sine theta. And then we want to find dx. There we go. And then I'm going to work out this thing here so that I'm ready to replace it. So a squared minus x squared equals a squared minus this thing here squared. And now I can use the identity that I chose and I'll get a squared cos squared theta. Sorry. Okay, so let's replace all of these things in here, so we get rid of the x's. So dx is going to turn into an a cos theta d theta. And the a squared minus x squared here is going to turn into a squared cos squared. Okay, and now we can do some cancelling. So the a's can come out the front of the integral, and one of them is going to cancel out on the top and the bottom. Okay, now here I've got a cos and a cos squared, so one of those will cancel out, and I'll just get left with 1 over cos theta d theta. Now 1 over cos is the same as sec, right? So this is 1 over a, whoops. Okay, all right. So what you have to do is you have to pick a substitution, do the substitution, and simplify it. And as soon as you've simplified it, you should just stop for a moment and say, is this something that I can integrate, either straight away or by using just one of the trig identities? Is this something we can integrate straight away? It's not. If it was sec squared, we could integrate it, because that would just be tan then. but it's not, it's just sec. Sec you can integrate, I think, with integration by parts, but it's really hard and quite long. All right, so we're going to say that that's too tricky. We're going to abandon that, and we're going to choose the hyperbolic substitution and see what that looks like instead. Too tricky. Okay, so we want the tanh one, right? Okay, so we're going to try the tanh one. The a squareds match, the minus matches. That means x squared has to match this thing here. So x has got to be a tanh. I know it should have a c, but it doesn't. Which one? Sech. Like that, yes. Sorry, yep, should be. Good pick up. Sech squared. Okay, so now we want to replace this thing here, so I'm going to figure out what it is. A squared take x squared is a squared. Tanh, bless you, sech squared theta. Okay. So now we know what to put in for our a squared minus x squared, and we know what to put in for our dx as well. All right, so dx is a, and a squared minus x squared is this thing here. Bless you. Okay, so you can see this one's going to be really easy, right? So the a's can come out and do a little bit of cancelling. If we simplify this, we've got a sech squared and a sech squared, and they're both just going to cancel out, and you get the integral of 1 with respect to theta. And this is heaps easier than trying to integrate sec theta. Okay? Heaps easier. Okay, and now we've just got to change this one back to x. So what have we got? This one here, x equals a tanh theta. Plus c. There we go. Okay. So the point is, when you come to do a trig substitution, there's going to be always two choices, one from the trig set and one from the hyperbolic trig set. And you're not going to know in advance, I can't tell in advance, if somebody figures it out, let me know, which of these to choose. Okay? The point of the story is, pick one, do your substitution and simplify. If it turns out to be something you can integrate, just do it. If it turns out to be something that looks hard or you're not sure, just do the other one. And then when you get them both simplified, so that would be this one and this one, look at them both and see which one's going to be easier to integrate. And it should be easy to just do it, or maybe you can just do one trig identity substitution. All right. Does anybody have any questions about that? No? All right. Bear with me for a minute. Yeah.
6, the circle. When you used your boundaries of A on 2, 0, didn't you have to top it and answer by 2?
We did. We cancelled the 2 into the fraction. Yeah. Okay. Thinking and thinking. All right. Give me 5 more minutes and then we'll have a break and then you can talk as much as you like for 10 minutes, all right? 5 minutes. That's all I ask. And then another 50 minutes after that. Okay. I was just trying to look through. We're going to miss a couple of examples. I was just looking which ones we'll miss. Okay, so this one's got an x squared minus a number. The number just turns out to be a squared. That's okay. So which one will we use? X squared minus a number. Which one from here? Beautiful. Someone said that with a very loud voice. Very good. And which one from here? Gosh, I'm giving out lollies now. All right. Ready? My throw was okay. I threw that one all right. Okay, we're going to use this one, the trig one. Okay. A squared sec squared theta take a squared equals a squared tan squared. So use that identity and multiply the whole thing by a squared. Okay, the a squareds match up, the minus sign matches up. That means x squared's got to be this thing here. All right, dx equals... Now, the derivative of sec is tan times by sec, and that's on the formula sheet, or you can just rewrite this as 1 over cos, and then you can differentiate it yourself, whichever one you like. But it's sec theta tan theta, d theta. And then we've got x squared minus a squared, and that is going to be, using this one, and use your identity. And then you're ready to substitute everything in. So I've got the integral. Dx is going to be this thing here. And on the bottom line, we get this thing here. Three halves. Okay. Now, you have to simplify this, and I strongly advise you, if you've got tan thetas and sec thetas in your little expression here, turn them all into sines and cosines, and then you'll be able to see which ones are going to cancel out. Okay? So I'm just going to deal with the a's first. So this a can come out the front, and this a here, I've got an a squared. The 2 on the bottom line means a square root, so that gives me an a, and then I want to have the third power of that, so that's a cubed. Okay, now sec theta is like 1 over cos. Tan theta is like sine over cos. And here I've got tan squared. I'm going to square root it and raise it to the third power. So I've got tan cubed on the bottom line, and tan is like sine over cos. So that would give me 3 sines on the bottom line and 3 coses on the top line, and then I've got a d theta. So once you've changed everything into sines and thetas, it's much easier to see which ones are going to cancel out. Okay. So what have I got here? I should have 1 cosine on the top line left. And on the bottom line, I should have 2 sines. Okay. So now we've done our substitution, we've done our simplification, so now's the time when you have a look at that and say, is that something you can integrate? It must be, because I told you this was the easy one. How are you going to integrate this one? Yeah, he said that. You can have a lolly too. We're going to do a U substitution. What's going to be our U? What's going to be our U? Sine? Yeah? Sine theta. So this is what we're going to replace, cos theta d theta. Now we can do this little integral, okay? So what do we get? We get 1 over a squared. This will turn into 1 over u with a minus sign out the front, plus c because it's an indefinite integral. Okay, so this is our answer in terms of u, but we actually want it in terms of x. So we're going to have to go from u to theta, and then from theta to x. Okay? Now u is sine theta. We're going to use this one here. Now we want sine theta, but we only really know what sec theta is. So now we get to choose between the little triangle and the trig identities. And none of the trig identities connect sine and sec, so I'm going to use the triangle. Okay? I haven't forgotten about the break, but we'll go a bit later. All right, so this tells us that cos theta is a over x. Because sec theta is just 1 over cos theta. Now cos can always hide. So if I draw my own little triangle, and this is theta, the adjacent one should be a, and the hypotenuse one should be x. And then I can use Pythagoras to get this one. Hey look, that's what was in our problem to start with. It will always come up like that, always, always. Alright, sine theta equals opposite over hypotenuse equals minus 1 over a squared. Now I actually don't want sine theta, I want 1 over sine theta, so I've got to tip this one upside down as well. Plus c. All done. Okay, so we had 2 back substitutions to do on that one, from u to theta and then from theta to x. Does anybody want to ask any questions about that one? No? Okay. All right, let's have a break, and it's 3 past, so we'll come back just after 10 past, all right? Go and stretch your legs and talk about whatever you want to talk about now before we come back and ask you to be quiet. fine. The triangle that I drew over here, this one here. Okay, now you know when to use it. What you have to do here, this makes sense, right? Because I've got to go from u to x at the end, right? So I go from u to theta, and now I've got to go from theta to x, okay? Now I want to know something about sine theta. And all I know, I can tell you what sec theta is, but I don't know anything about sine theta. So there are two ways to kind of link these two together. One is by using a triangle, where you can use anything as a triangle. The other way is by using a distance. Right, now, if you look at those identities there, there's not an identity that's got sine theta and sec theta in it. So what you have to do is if they're not shown by nodes, then it's easier to who is that? Oh, okay. So I was going to go through the ones on the line, and if anyone doesn't have a partner and I can't join them up, then I was going to get a third. Okay, so you're happy to have a third. But it depends if there's anyone left.
Forget about the inverse the second sense. You know what I mean? When you go 1 over cosine, I think you flip it around. Because then you get the secant will be the height over the distance. You know what I mean? Yeah, but that's not the same thing. Now, it's just two separate triangles, it's just two separate sides of triangles. Oh, hang on. That is important. If you take the cosine of both sides,
And you get one, and I noticed the same thing. It was like
you get the cosine of the cosine of that.
you said that.
Maybe that's it. That's right, yeah, it comes up like cosine is I mean, sorry, you can't this by cosine, then you get cosine. Not just no, because that, not cosine, yeah, sorry, you just get that, and then cosine is that, that's how you get that. Use that. There you go. You can use those
All right, let's get cracking, shall we? Was there anybody in that little area there before, or am I just imagining it? They all left. Oh, pardon? They're the hide and seek champions, yes. Behind the curtains, maybe. Okay, which one have we got today? What has mathematics got to do with making babies? Well, this is what I was going to say. Who's talking? You guys up there? Okay. It's not because I'm a mathematician is a great pickup line, although you'll be surprised. When I was at Adelaide University, I was working with somebody who had a separate project. She was approached by one of the professors in obstetrics and gynecology, and they were doing stuff with IVM. So you probably have heard of IVF. And IVF is in vitro fertilisation. So what they do is they give the hopeful mother a bunch of drugs, and it makes her eggs mature, and then they can get them out, fertilise them, and put them back in again. So it's in vitro fertilisation because they fertilise the eggs outside. What they were wanting to do is in vitro maturation. So the trouble with that is that the drugs that they give the mother are not very pleasant, and they're very expensive. So they wanted to do away with that. Harvest and take the immature eggs and then mature them outside of the body, so that's the in vitro maturation part, then fertilise them and put them back in. But the trouble was, when they took these things out and they weren't mature, they didn't know how much oxygen they would need, and they didn't know how much nutrients they would need and that kind of thing. And they're doing all these experiments, I think mostly with bovine eggs, and they couldn't get them to work, so something was clearly wrong. So they came to her and they said, can you help us? Now this thing here is the cumulus oocyte complex. This is the little egg here, and around it are all these cells, and they can measure the oxygen and the glucose and stuff at the edge of this, but they can't measure it in here, and that's what they wanted to know. So they came to Yvonne, and Yvonne did a bunch of calculations, and the levels of oxygen that they were giving these eggs were completely inappropriate. And that's why they were all dying. So they changed how much oxygen they're giving the eggs, and now they can mature them. So they're keeping on progressing this until we can get in vitro maturation for humans, I guess. So there you go. So that was a really successful thing to happen. It made a big difference for them. Okay. What are we doing now? More examples. Just did 38. All right, I'm going to skip a bunch of examples, but I'll put the solutions on the web. Pardon? Oh, where's the solutions for the questions I don't know? So there's a folder where you get the lecture notes from. So I'm putting them in there. On the study materials page, I think. There's a little tab called study materials, and in there is a folder for the lecture notes. And in there's the lecture notes, and I'm putting the extra examples in there. Okay? All right, so we're going to miss 39. We're going to miss 40, 41, 40. Oh, we're going to do 42 and 43. Here they are. Did you bring lunch for everybody? A hot chicken? Oh my gosh. You did. My goodness. I should have this rule, and the rule should say, no hot chickens. The rule should say you can bring your lunch as long as it doesn't smell delicious and make the rest of us hungry. I think that's what it should be. You guys. Okay, this is the example we're going to do next. The reason I picked this one is because it has a number that's not 1 in front of the x squared, so this one's a little bit different. Okay. When you get a problem like this, where the number in front of the x is not a 1, my strong advice is, you don't have to do this, but this is my strong advice, get rid of that 3. Okay, because it's hard to deal with, so let's not deal with it. So, oh, you guys, is that a packet of M&Ms? Oh, I haven't eaten. That's not very fair. All right, so what we're going to do to get... Not right now, thank you. All right, I'm going to take a factor of 3 out the front on this denominator. That means I'm going to have a third there and an x squared there. Okay, and so now we've got something that looks like all the problems we did before. There's a 1 in front of the x squared, and I can just deal with that 3 at the end. And over 3. Okay, oops, dx. Okay, so now we've got to pick a trig substitution. Which one will we pick? The tan squared. Yeah, we're going to pick the tan squared or the sine squared. In this example, the tan squared one works the best, so that's what we're going to use. And we have to multiply the whole thing by 1/3, okay? One third sec squared theta. Okay, so the third matches up, the plus matches up. That means x squared must be this thing here. So x is going to be 1 over the square root of 3 tan theta. Okay, now we need to substitute for dx, so let's figure out what that is. There we go. And we need to substitute this thing on the denominator. So it will be a third plus, now x squared. X is this thing here, so that gives us a third tan squared theta. And now I get to use the identity that I picked and change that into a third sec squared. No? Okay. It's possible, but no, not this one, I think. So the point of doing this is we've changed this thing here, which is a sum of 2 things, into this thing here, which is a product of 2 things, and then it's easier to integrate. All right, so this 3 here I've taken out the front. The denominator here is going to get replaced with a third sec squared theta. The dx gets replaced with a 1 on root 3 sec squared d theta. Okay, so we can take all the constants out the front. This 1/3 and this 1/3 will cancel each other out, and I'll get 1 on the square root of 3. Oh, I didn't put my bounds in. That's a bit naughty. X equals 0, x equals 1. Make sure you say x equals, because it's not theta equals. Okay, and this one here, what happens here? Bless you. Sec squared on the numerator and a sec squared on the denominator, so they're going to cancel each other out, and I just get 1 d theta. So this is the right one to choose, because the integration part turned out to be easy. Okay. So now we can either change the theta into x's, or we can change the x bounds into thetas. I am going to change the x bounds into thetas. So when x is equal to 0, use this thing here, and we get 0 equals 1 on root 3. Theta equals 0. And now the 1, 1. Oops, off the page. Okay, tan theta equals the square root of 3. Now tan, some odd hairs can always hide there, old age. So tan would be opposite over adjacent, and we want opposite over adjacent to be the square root of 3. If we look here, here's the square root of 3. Opposite over adjacent would be the square root of 3 divided by 1, which is just the square root of 3. So this one should be the opposite, this one should be the adjacent, and that will give me theta is pi on 3. Okay? All right. Done. Is that really the time?
Where you cancel out the 2 sec squares, if
Mm-hmm.
that was equal to 0, you couldn't do that? Or
If which was equal to 0.
the sec squared, if that was ever equal to 0?
Ah, that's true. Yes, that is a very good question. So, in this case, it never can be 0 because sec is equal to 1 over cos. And so that can never be 0 because you've got 1 on the numerator. But you can do examples where you have something different here and it can equal 0. So that will only be a problem if the place where it equals 0 is within these bounds. Okay? And so after we've done techniques of integration, we talk about improper integrals and we talk about it more there. Okay? But that's a good question. Yeah. Does anybody have any other questions? Yeah. How did I get 3 times this one here? So what I did was I didn't want to deal with a 3 in front of the x squared, so I took it out the front of some brackets, and then I knew that it would be gone from here, and 3 times a third makes 1. You're kind of just engineering it to be something that you'd rather look at. It's exactly the same, but it's in a kind of a nicer form. Yeah. Does anybody have any other questions? Yes. Can you substitute y is equal to the square root of 3x? Yes, you can. Yep, but you have to make sure you also change it from a dx to a dy, and that's going to give you a square root of 3 coming out in it as well, and that's fine. But you have to make sure you back substitute when you're doing the bounds, I guess, would come in this question. Yep, that would be fine too. Does anyone have any other questions? No? Okay. All right, in the interest of time, I wanted to do the next one, but I'm going to miss that out as well. And the next one. All right, we're going to zip on to this one here. I think I made too many examples in this section. Okay, let's do this one here. And then after this one, I'm going to talk about something a little bit fancier you can do with the trig substitution. Who's talking? You three there are talking lots. Just, that's enough. Had enough. Okay, in this example here, all we're going to do is write down, crikey, my hand's huge. All we're going to do is write down the two different substitutions that you could use, and then I'll tell you which one is the easiest, and you can go home, and if you're looking for something exciting to do, you can do that. All right, here's a question here. What substitution could you do for this one? X is equal to what? What would be the trig substitution you would do? Think carefully, because that 12 and the 3 are going to throw you off. What would be the substitution? Which trig one? Well, let's pick a trig one first, and then we'll figure out. This one? Very good. Now, what would be the exact substitution that you use? Do you know? 4. Who said 4? You're so close, but it's not 4. Not that close. It's going to be a 2, right? And I'll tell you why. What you would do first is you would take a factor of 3 out of here, and then you would have 4 plus x squared, and then you want to take the square root of that. Ah, yeah? You want to take the square root of it because x has got to be equal to this thing here with a 4 out the front. So the square root of that would be a 2 tan theta. And the hyperbolic one, sine theta. Okay. All right, this one here, which substitution would you do for this one? Which trig one? The sec squared one, yeah. You would have x is equal to what? The sec squared one, yeah, sec squared 1, but x is equal to what? Anyone? Yeah, beautiful. You can have a lolly. Square root of 5 sec theta, and so the hyperbolic one is going to be the cosh one. Whoops, not squared. Cosh theta. Now, Damien, did you say sec theta? And then Jonathan, you said square root of 5. I'm handing out lollies for those who didn't bring lunch. I forgot to tell you which was the easiest one. This is the easiest one here, and this is the easiest one here. So if you want to, you could go and do this one or this one, and you can see what happens if you pick the wrong one. All right, what would be the substitution here? 4 tan theta. Yeah, you could, if you're a glutton for punishment. Ooh, that's what happens when you bring in lunch. Ah, yeah, you can have a lolly. U substitution. That's an easy one. Well, not an easy one. That's a U substitution, right? So, the moral of that story is, look for the easy technique of integration before you go for the hard one. But you could do it with a 4 tan theta. That would work. It would just be more work. All right, what would you do for this one? What's it going to be? It's going to be a sine one, right? Everyone's too tired now. 2 sine theta, or x is equal to the tanh one, right? And which is the easy one? This is the easy one. Okay, we're not going to do the integral in t because there's something else I have to tell you before we go. Does anyone want to ask any questions? Yeah. Can you do the last one by parts? Maybe, because you've got a derivative here if you take one of those x's, but off the top of my head I don't know how hard it would be, but yeah. Does anyone have any other questions? No? Okay. All right, now you get to listen to me for a little bit. Isn't that exciting? We're not doing those, we're not doing those. Okay. All right, listen up. As soon as I say you have to listen to me for a minute, everyone gets their phones out. That's just great. Okay. All right, for this integral here, what are we going to do? This integral here. So this is kind of what we've been dealing with, something like a quadratic under a square root sign or something like that. But this one has got like the x term. So the ones we've done so far have had like a constant and an x squared. And this one just has the x squared and an x term. Now, what you have to do is something called completing the square. Who did completing the square at school? Some, but not many. Okay, completing the square. Now, I'm going to go through this and show you what you have to do, but I think it's easier if you actually just do it. See how I've got 2x minus x here? I'm going to turn this into a quadratic that we're used to seeing. So we're used to seeing a quadratic with an x squared without a minus sign, right? So that's like this one. So that would give me an x squared minus 2x. So that's the original expression just there, right? Now what you want to do is you want to turn this into a perfect square, okay? So you know how when you have a perfect square, watch this. You know when you have a perfect square, you have x plus a squared. Okay, this is, don't throw food around. You have a perfect square, right? So you do the square of the first, and you do the square of the second, and then you do twice the product. Maybe I should write 2ax there. 2ax, okay? So what you want to do, you want to make a perfect square, so you want to follow this pattern. Now I had an x squared minus 2x, so that tells me that the a in this case is going to be minus 1. So if I put minus 1 squared here, right, a is equal to minus 1, that's going to give me a perfect square, but I'm not allowed to change the question, so I better put a minus 1 there, okay? And that's exactly what I've done here. I've added this 1 inside these brackets to make it so that this thing here looks like a perfect square, but I'm not allowed to change the question, so I've got this plus 1 here to cancel out the bit that I added, because this plus 1's got a minus out the front of its brackets. Okay, so you make it look like a perfect square, and then you factorise it and turn it into something like we're used to. Okay, this just says the same thing, so I'm not going to go through it. All right, the only thing I want to say is you can do questions like this as well, so you don't have to have a square root sign. If you get a question like this, before you do it with a trig substitution, you should check if you can do it by partial fractions, because partial fractions is easier. Partial fractions is what we're going to start on Wednesday, okay? So you have to do this by partial fractions if you can factorise the bottom line. Otherwise, you can do it with a trig substitution, okay? All right, we're going to do 2 examples, and then you'll be free to go. How exciting. Yes. Okay, so this has got a quadratic on the bottom line, so it doesn't look like what we've been doing. Far out there. Okay, so what I want to do is I want to turn this into a perfect square, okay? So if I want to turn it into a perfect square, x squared plus 2x plus 1, that's a perfect square. Yeah, plus 2. I can't change the question though, so I have to make sure both sides are the same, and I can do that by putting a plus 2 there. Okay, because now altogether I've got a plus 3. All right, x plus 1 squared plus 2. So now I've got something like what I'm used to having, something squared plus a number. So that's going to be like this. Which one is it? This one here. Something squared plus a number. Okay? All right, so now that we've done that little bit of work, okay, so now what I do is I turn this one into a u. So I'm going to say let u be equal to x plus 1. So it's not like a u substitution like we know u substitutions to be. We're just using u. And don't forget, you've also got to change the dx. So du is equal to dx. All right, so that part doesn't change. Well, it changes into a u, doesn't it? Okay, so now we get to choose which trig substitution we're going to use. Which one will we use? Pardon? That one, yeah? Or this one, right? This time this one is the easiest one, so that's the one we're going to use. All right. So we're going to use, which one did I say? The shine. Cinch. Actually, some people do say cinch. All right, multiply it by 2. Okay, so we have to change the du as well. So that's the du taken care of. And now we have to figure out what the u squared plus 2 is going to be. U squared plus 2, use this one here. So u squared is going to be 2 sine squared theta plus 2 equals, and then we use the identity and we get 2 cos squared theta. So we've changed the thing under the square root sign where you've got two things adding together, which you can't really deal with, to just a multiple of two things. All right, du, what have we got? Square root of 2 divided by there we go. All right, and you can straight away see this is going to cancel out nicely. Okay, so the 2 square roots of 2's are going to cancel out. The cosh, this is going to be a cosh on the bottom line, a cosh on the top line, they're going to cancel out. So everything works out easy, and we know we chose the right one. So what do we get? Theta plus c. Okay, so there's our answer in terms of theta, but you have to write it in terms of x. So we're going to use this one first to change it from theta to u, and then we've got to do this one to change it from u to x. Okay, so what have we got? Sine theta equals u on the square root of 2. Now u is equal to x plus 1. So that means I can replace theta with arc sine plus c. That's it. Does anybody want to ask any questions about that one? with arc shine and stuff. If I gave you one that I wanted you to work out, it would be one like 0. Who's talking? If I gave you one I wanted you to work out, it would be like 0, and then you can just do like e to the 0 plus or minus e to the minus 0, and you can work it out. If it's anything else, like a 4 or a 2 or a 5, you just leave it in brackets like arc shine of 4. That would be it, okay? Because you can, you can't. You can, if you know what the log function is, you know how you can write it in terms of a log. You can stick it in there and play around with that, but really that's not what I'm trying to teach you, how to fuss about with stuff like that. All right, does anybody have any other questions? No? All right. This one. Whoops, haha. Okay, so this one's got a quadratic on the bottom line underneath the square root sign. So to make this into something we can deal with, we've got to do a complete the square, so we can get a number and a something squared, and then we can do our trig substitutions. So let's have a look. Okay, so the x term and the x squared term are the parts you want to use to complete the square, right? So if we follow this little principle here, we've got an x squared, and what have we got? Minus 6x, so that tells us that a is going to be minus 3. Minus 3, right? And minus 3 squared is 9. But you're not allowed to change the question, so I'm going to do minus 9 minus 7, the 7 that was there before. Okay, so I added 9 because that was convenient, and then I have to take it away so I don't change the question, and then I've got the 7 from before. So then I get x minus 3 squared minus 6, oh that's terrible, 16. Plus 6x. Which one? There. Oh, it should be. I was looking at that. That was silly. All right, so we want to add 9 still, and then we want to minus 9. Yep. Yep, you're right. Okay, and now we should put this minus sign back inside the brackets, which is just going to switch the order of things. So 16 minus x take 3 squared. Oh, yeah, it does. Sorry, thank you. Okay, all right, so this looks more like what we've been dealing with all day. Let u be equal to x plus 3, and then du is equal to dx. Okay, and so now we can do our trig substitution. 16 minus u squared. Which one do we want? Yeah, we want the sine squared one at the top, or we want the tangent one at the bottom. Okay, and the sine squared one's going to be the easiest one. So I'm going to multiply it by 16. 16 minus 16 sine squared theta. Okay, so the 16s match up, the minus matches up. That means 16 sine squared has got to be u squared. So u is going to be 4 sine theta. Okay, 16 minus u squared is 16 minus, now here is u, and now I get to use the identity that I picked, and that's going to be 16 cos squared theta. You guys are so unfair. Divided by... Okay, so we've got a 4 on the top line and we've got a square root of 16 on the bottom line. Those are going to cancel out. We've got a cos on the top line and a cos squared square root on the bottom line, so those are going to cancel out as well. And now it's really easy. Okay, so that's our answer in terms of theta. But we can't leave it like that because those kind of bad manners will cost you about 3 or 4 marks in the exam. So you have to change it back, or maybe not 3 or 4, maybe 2 in this one. You have to change it back to an x. So what have we got here? In this one here, I've got sine theta equals u on 4. And then in this one here, I know that u is equal to x plus 3. So I just have to take the arc sine of both sides here and I'll have what theta is. Oops, plus c. Done. Okay, does anybody have any questions about that one? So we finished 10 minutes early, so let's go back and do one of the ones I missed. No, I'm kidding. I'm kidding. Okay, that's the end of trig substitution. So this week's shoot, I think, is mostly practicing this kind of stuff, all right? That's all I want to say. I'll see you guys on Wednesday and we'll start the next one. Have a good couple of days. Yeah.
How many marks did that last question include? 2 marks for not converting back to X. How many marks did the actual question include?
And then the whole
Are you going to be in your office for a bit? Because I sent my assignment and apparently my tutor, because I wasn't there to get it back from you. Last week he said that he's getting it back to you.
You only get one chance.
Are you going to be in your office
I
for a
will,
bit?
but I just have to go past the unit and then I'll be in my office. So like 10 minutes I'll be back. Depending how long I am here. But
That's right. And you think you're going to be there for a while?
I'll be there at least until 4.
Okay, sweet.
Yeah.
Question. This solution is
Sorry?
this solution is for the teacher. It's not for you. And I'm from the 7. Yeah, Gary. Yeah. But I'm not sure this one is.
Okay, so how did you get from here?
Yeah.
Yeah, but, So the question I have for him is how do you go from here to there? And I expect, I mean, you can see there's 1 sec on the bottom and 2 on the top, right? This is going to be the integral of 6 theta. He gives a different formula sheet to mine, and he will apply that formula sheet.
But how he used the link to the law you use to solve the question?
So the integral of sec theta is log of sec plus tan, and that's something that's really hard to figure out. So this step will have been on the formula sheet, and then he will have changed this back. Where's the substitution? Here. So he's got tan theta here. It's going to be mu on root 2. And mu equals h plus 1. So he's changing that. That's that one there. Right. And the sec theta here, he's done it with a little triangle like I was. And put that in there.
So you use the way and this way is always correct.
Well, yeah, so both of them would be correct, but this way, I mean, so what our answer, so we got this one, right?
Yeah.
How come yours says 22? Oh, this is his note. Oh, this is my old note. Okay.
Yeah.
So he did this, we did a hyperbolic substitution, right? So you know how you can write the inverse hyperbolic function in terms of logs?
Oh. So also I can write like this way.
Yeah, so somewhere in here, way back, yeah, there's the arc cost one. Yeah, arc shine, you can write it in terms of logs. So I've written it as an arc shine and he's written it as a log. This technique, you cannot do it without a formula sheet because this step here is really tough. Okay, so he's chosen to do it with the trig substitution and then it works out to be really hard. I chose to do it with a hyperbolic substitution and it works out to be really easy. So one will be hard and one will be easy.
Yeah.
Okay, and you can decide that this one is hard when you get to there and you can decide that this one is easy when you get to there. So that's how much work you do before you think, oh, this is too hard.
Okay.
So I would say that's too hard, I'm not doing that, I'll do it with a hyperbolic substitution.
Okay. Thank you.
Yeah? Okay, no worries.
Just
So,
quickly,
yes.
good. I'm not here currently.
Yeah.
I'm away. This was a couple of weeks ago. There was a plan for us to go home for the day.
Okay.
I won't be with the tube, and my computer practice tomorrow along with Gabriel's.
Okay.
You said to come later in the week,
Yep,
just so we don't get marked.
that's fine.
So,
Yeah, so we're not marking, I don't mark attendance for the 2 weeks when you're working on the project because lots of people swap pracs because they go to their partners instead. So keeping attendance is just too hard. So you won't be marked, you'll probably be marked absent, but that one won't get counted towards
does that go towards our marks?
absence. Only like a small, tiny little bit. Almost often.
Okay.
Yeah. So it goes towards your MATLAB score. So you'll get a score out of 4 for attendance and doing stuff, and then you get a score out of 100 for your project, and I combine them. So the 4 is like some small fraction. Yeah. That's all. Yeah.
Airplanes there. So,
Okay. Sure.
so we'll probably
We'll have
slowly-
fun.
I will.
Is it for something fun? Hopefully.
We own a bakery,
Oh,
and it's
nice.
been Australia's best pie. And
Meat pies.
no, vegan.
Oh, so
Vegan
what's in it?
restaurant. Lentils. Lentils. It's like a lentil curry pie
How do you make the pastry?
with a vegan pastry, like a vegan humble pastry.
But what do you put instead of butter?
But no. It's a you've got me. I don't know. I'm not a baker.
Okay.
It's a not a margarine. It's a
Oh, yeah, you could use
it's a
like a
vegetable.
margarine.
It's
Like a,
it's vegetable.
like a-
hard vegetable oil.
yeah, okay.
So
That would be hard to get right, I guess.
No, we've done pretty well. It's our
Okay.
biggest thing.
I'm not saying you didn't do it well, I'm
No,
saying it
we've
would
had
be hard to
yeah,
get
it was.
right.
It took 3
Yeah.
years, and we've got to where we are now.
Okay. Cool.
And we threw in like a curry potato, a Cornish, and a sausage roll. It was like
Cornish
100
pasty, they're my favourite.
They're really good. It was like $180 to send them over by courier. It was $60 a piece to send them over.
Bloody hell.
My flights cost me $200, and I can at least they get there safely.
Yeah.
They don't get there damaged.
Oh, you're actually taking them then? Yeah.
Over the carriage.
Yeah,
So
okay.
flying out, you can fly back in.
Oh, good luck.
That's
Hope it
awesome.
goes well. Cornish pasties are my favourite. My grandparents lived up at Moonta. Yeah, that's where they started. And there's a bakery there that's got some secret recipe.
We make nice pastry. Our pastry's alright. Our pies, everything's good.
Yeah.
Like I said, shit.
So which bakery is it?
Continental Bakery. South American pies. South American pies.
Yeah.
And crochet.
Yeah.
It's more of a wholesale bakery.
Oh, okay, right.
So little activity that's done in uni stay in town, they're running in town. We try to bring it here, they take part of it.
Oh, which one was that?
But they're really small. It was the one at uni stay,
Yeah,
Sydney, City
yeah.
West, and we do each big one. So we start down, and at uni it's a lot. A lot of vegans,
Yeah.
a lot of Muslims
Yeah, yeah.
that are eating meat,
Yeah.
so I'll bring a pie.
Pardon?
I'll bring some pies sometime.
Then I can eat them while everyone else is having their hot chickens. Yeah. Cool. All right, well, good luck. Have fun. Yeah, no worries. See ya.